Every C++ developer, at some point, writes a line of code that looks perfectly fine, like int x equals 3.14 semicolon. It compiles, maybe with a warning, and then x quietly becomes 3. You lose data, and the program keeps running. But then, you try int y curly brace 3.14 curly brace semicolon, and suddenly, the compiler screams at you with a hard error. Why? Why does one silently truncate your data, while the other refuses to even build? This isn't just about different syntax. It's about a fundamental difference in how C++ treats your intent and how it protects you from yourself. Today, we're going to unlock this critical distinction. When I first ran into this, I spent hours debugging a subtle calculation error, only to find it was a silent type conversion. So, to save you that pain, we're going to master how C++ interprets the raw data you type into your code, what we call literals. We will navigate the labyrinth of C++ initialization techniques: copy, direct, uniform, and value initialization, understanding their subtle yet crucial differences. You will learn to leverage auto for cleaner code and decltype parenthesis auto parenthesis for perfect type forwarding, ensuring your types are exactly what you expect. Most importantly, you will prevent critical pitfalls like those silent narrowing conversions and the infamous most vexing parse. Let's start with literals. Think of literals as the raw, unadulterated data you embed directly into your source code. When you type 42, 3.14, or you are writing a literal. The compiler doesn't just see a sequence of characters. It immediately assigns a type to that literal based on its form and any suffixes you provide. This implicit typing is crucial because it dictates how the literal is stored in memory, how much space it occupies, and what operations are valid on it. For example, 42 is not just a number. It is an int literal by default. This means it will occupy 4 bytes on most 64-bit systems, and its maximum value is typically around 2 billion. But what if you need a larger integer, or an unsigned one? C++ provides suffixes to explicitly specify the literal's type. If you write 42L, that L suffix tells the compiler this is a long integer, which might be 8 bytes on your system, allowing for much larger values. 42LL makes it a long, guaranteeing at least 64 bits. For unsigned integers, you append U, so 42U is an unsigned int. You can combine them, like 42UL for an unsigned long. Floating point literals also have this behavior. 3.14 is a double by default, which offers about 15 to 17 decimal digits of precision. If you need less precision and potentially less memory, 3.14f explicitly makes it a float, typically 7 to 8 digits of precision. Let me show you how these suffixes change the literal's type. I'm going to use type ID parenthesis .name parenthesis, which gives us a string representation of the type. Don't worry about the exact string output, as it can vary between compilers, but the underlying type will be consistent. Here, standard cout left shift type ID parenthesis 42 parenthesis .name parenthesis left shift standard int L semicolon will show I or int for the default integer. Adding L to 42L will output L or long int. The LL suffix for 42LL gives us X or long int. For unsigned, 42U will be J or unsigned int. For floating points, 3.14 is D or double, and 3.14F is F or float. When you run this, you will see the compiler's internal representation of these types, confirming that these suffixes are not just comments, they are type specifiers. The output will look something like this: I, L, X, J, D, F. This confirms that the compiler is indeed interpreting these literals as distinct types. The common mistake I see people make is assuming 3.14 is a float because it has a decimal. It is not. It is a double. If you then assign it to a float variable without the F suffix, you are implicitly converting a double to a float, which can lead to precision loss. This is a subtle point, but it can cause significant bugs in financial or scientific applications where precision is paramount. Now that you understand how literals get their types, initialization is going to make perfect sense. Initialization is the process of giving a variable its initial value when it is created. This is distinct from assignment, which changes a variable's value after it has already been initialized. C++ offers several ways to initialize variables, and understanding their nuances is critical for writing robust code. The oldest and most familiar is copy initialization, using an equals sign. It looks like an assignment, but it is not. It is setting the initial value. Then we have direct initialization, which uses parentheses. This syntax is often seen with constructors for class types. Since C++11, uniform initialization, using curly braces, has become the preferred method. It is designed to be, well, uniform across all types, and to prevent certain common pitfalls. Finally, there is value initialization, which also uses curly braces, but empty ones. This form guarantees that the variable is 0 initialized or default constructed, which is a crucial safety feature. Let's look at these different forms in action. I will declare 5 integer variables, each initialized with the value 5 or 0 for value initialization. Here, int a equals 5 semicolon is copy initialization. Int b parenthesis 5 parenthesis semicolon is direct initialization. Int c curly brace 5 curly brace semicolon is uniform initialization. Int d equals curly brace 5 curly brace semicolon is also uniform initialization, sometimes called copy list initialization, and it behaves identically to int c curly brace 5 curly brace semicolon for fundamental types. Finally, int e curly brace semicolon is value initialization, which will set e to 0. When you print these values, you will see a, b, c, and d all hold 5, while e holds 0. The output will be 5, 5, 5, 5, 0. Here is where uniform initialization really shines, and why it is preferred in modern C++. It prevents what we call narrowing conversions. A narrowing conversion occurs when you try to implicitly convert a value from a type that can hold a wider range or more precision to a type that cannot. Think of trying to pour a gallon of water into a pint glass. You are going to lose information. Traditional copy and direct initialization will often allow this, sometimes with a warning, but uniform initialization makes it a hard compile time error. This is a safety net, catching potential data loss before your program even runs. Let's revisit our initial example. I will show you the problematic code first. With int x equals 3.14 semicolon, the compiler performs an implicit conversion from double to int. It truncates the decimal part, and x becomes 3. You might get a warning like, warning, implicit conversion from double to int changes value from 3.14 to 3. This is a silent data loss. Now, if you uncomment the next line, int y curly brace 3.14 curly brace semicolon, and try to compile, you will get a hard error. The compiler will stop you dead in your tracks, saying something like, error, non-constant value cannot be converted to type int in narrowing conversion. This is uniform initialization doing its job, preventing you from accidentally losing precision. Another critical problem uniform initialization solves is the most vexing parse. This is a classic C++ ambiguity where the compiler cannot tell if you are declaring a variable or a function. It is particularly common when you are trying to default construct an object without arguments. The compiler, by rule, always prefers to interpret something as a function declaration if it can. This means your innocent-looking object creation might actually be declaring a function, leading to bizarre compilation errors or runtime behavior because the object you thought you created simply does not exist. Let's illustrate this with a simple widget struct. I will define a basic struct and then show the vexing parse. Here, struct widget curly brace semicolon is just an empty type. If you write widget w parenthesis semicolon, the compiler interprets this as a declaration of a function named w that takes no arguments and returns a widget. It does not create a widget object. If you then try to use w as an object, you will get a compile error like error, call to non-static member function without an object argument. The fix is to use uniform initialization. Widget w object curly brace semicolon. This unambiguously creates a value initialized widget object. This is a subtle but powerful reason to prefer uniform initialization, especially for objects. Now that we have covered explicit types and safe initialization, let's talk about auto. The auto keyword, repurposed in C++11, tells the compiler to deduce a variable's type from its initializer. It is like saying, hey compiler, you figure out what type this is, I am just giving you the value. This is incredibly useful for long, complex types like iterator types or lambda closures, where writing out the full type would be cumbersome or even impossible. It can also improve readability when the type is obvious from the context, reducing visual clutter. However, auto is not a magic bullet. It performs what is called type deduction, which is similar to template argument deduction. Crucially, auto strips away references and top-level const qualifiers. So, if you initialize an auto variable with a const in ampersand, the auto variable will become a plain int. This is a common mistake that can lead to unexpected copies or loss of const correctness. You need to be aware of this behavior and explicitly add const or ampersand back if you need them. Let me show you how auto deduces types and where it can surprise you. I will declare a few variables with auto and then inspect their types. Here, auto I equals 42 semicolon will deduce I as an int. Auto d equals 3.14 semicolon will make d a double. Auto s equals quote hello quote semicolon will deduce s as a const char star. Now, consider constant value equals 10 semicolon const int ampersand getref parenthesis parenthesis curly brace return value semicolon curly brace. If you then write auto x equals getref parenthesis parenthesis semicolon, x will be deduced as a plain int, not a constant ampersand. The const and the reference have been stripped. If you print type id parenthesis x parenthesis dot name parenthesis, you will see I4 int, not RKI4 constant ampersand. This is the critical behavior you must remember. This leads us to decltype parenthesis auto parenthesis, introduced in C++ 14. If auto is like asking the compiler, what type is this value? Then decltype parenthesis auto parenthesis is like asking, what is the exact type of this expression, including all its references and constants. It combines the convenience of auto's syntax for variable declaration with the precise type deduction rules of decltype. This is incredibly powerful for perfect forwarding in generic code, where you need to preserve the exact type, including its value category and qualifiers, from an expression. When you use decltype parenthesis auto parenthesis, the compiler deduces the type of the variable exactly as if you had written a decltype expression for the initializer. This means if the initializer is in value reference, the deduced type will be in value reference. If it is a const type, the deduced type will be const. It does not strip anything away. This gives you fine-grained control over type deduction, ensuring that the variable's type perfectly matches the expression it is initialized from. Let's revisit our getref example to see decltype parenthesis auto parenthesis in action, and also compare it with const auto ampersand. Again, we have constant ampersand getref parenthesis parenthesis curly brace return value semicolon curly brace. If auto x equals getref parenthesis parenthesis semicolon deduces x as int, then decltype parenthesis auto parenthesis y equals getref parenthesis parenthesis semicolon will deduce y as constant ampersand. If you print type id parenthesis y parenthesis dot name parenthesis, you will see RKI or constant ampersand. This is the exact type preservation we need. An alternative, if you know you always want a const reference, is const auto ampersand z equals getref parenthesis parenthesis semicolon. This also deduces z as const in ampersand. The choice between decltype parenthesis auto parenthesis and const auto ampersand depends on whether you need the exact type of the expression or if you specifically want a const reference regardless of the expression's original referenceness. You now understand three crucial aspects of C++ that will make your code safer and more expressive. First, you can precisely control the type of your literals using suffixes like L, LL, U, and F, preventing implicit conversions and ensuring data integrity. Second, you know why uniform initialization with curly braces is the modern C++ standard. It actively prevents dangerous narrowing conversions and elegantly solves the most vexing parse. Third, you can confidently use auto for convenience while being aware of its type stripping behavior, and you can deploy decltype parenthesis auto parenthesis when you need perfect type preservation, especially for references and constants. These techniques are fundamental to writing robust, predictable C++ code. Next time, we are going to dive into constants and compile time evaluation, exploring how to declare values that cannot change and how the compiler can perform calculations for you before your program even starts running.